So today we're going to look at dummy variables or categorical variables in R. Then we're going to look at some, what I'm calling advanced R techniques. So these are techniques that you may find helpful as you're completing your final papers. And then we're going to change gears entirely and do some sentiment analysis using R. We're actually going to take a news article that was written by TVO about the coronavirus, and we're going to take a look at it and see what kind of emotions does this article seem to evoke. Any questions before we start? Cool, let's get started. All right, let's talk about dummy or indicator variables. Suppose for a moment you want to investigate the differences between two groups. For example, in today's data set, we're taking a look at lung capacity for children and teenagers. And the way that our data set is broken up is we have a number of different groups. We have broken up by whether or not the child was born via cesarean section, gender. There's one or two other groups. And suppose we want to investigate, see if there's a difference between them. So we maybe want to control for for the male or female population. So it turns out in R, we can create dummy variables for our regressions. So how can we do that? Well, it turns out this is something that's really awesome. You're probably expecting right now that we're going to have to write some insane code to make the dummy variables work. We're going to have to generate a brand new column, right? Because that's what we've done so far. Wrong. If a column is interpreted by R as being categorical, in other words, it's factorized. Remember we talked about factors? Sort of, kind of. Basically, when R reads in one of your CSV files, if it sees a column of strings, if it sees just string values in a column, it's going to interpret those as categorical data. So for example, in our file, we have a column called gender, and it has either male or female. R will turn that column into a categorical column automatically. All we need to do in order to use that as a dummy variable is add that column to our linear regression model. And we're done. Cool, right? So like I said, today's example, we're looking at lung capacity data. And we're going to answer the question, what seems to have the higher influence on lung capacity? We're going to take a look at gender, whether or not the youth is a smoker, and potentially age range. So first things first, why don't we do a quick demo? We'll actually try to use the gender dummy variable and create a linear regression model that has gender as our dummy variable. First, why don't we take a look at the code? Or why don't we take a look at the file, the data file that we will be using. By the way, this has all been posted to Learn. It has not been posted? Hands up if you do not see it on Learn. Crap. All right, one moment. Just a second here. And the reason that, and you might notice, well, let's take a look at this data. So let's see, we have lung capacity, age, height, whether or not the person smokes, gender, and whether or not the child was delivered by cesarean section when they were born. Anybody notice something different about this file that we haven't seen before? Yeah. Well, the file extension is .txt. It's a text file, but are CSVs text files as well? Yeah, CSVs are text files. We've seen that. So if you remember, if we go back to, say, a previous week's data file, for example, if I go back to, say, week 3, and we open up a CSV file, we see that it, too, is just a text file. So nothing, so we're dealing with two text files here. Does anybody see, but what seems different? Let me put the two side by side. What seems different between these two files? I've got my old CSV file on the left, and I've got the new lung capacity data on the right. What seems different between these two files? Yeah. So there's no commas, which is interesting. It seems formatted differently. So here's the difference between these two files. Let me open this up in Notepad++, because with that, I can show you the exact difference. So if I look at the lung capacity data with Notepad++, whoops, oops, I don't want magnifier. Okay, so if we open this up with Notepad++ and take a quick look, and I'll zoom in a little bit here. If I view all the symbols, for example, the white space and tab, you'll notice that there's these little arrows that are between each of the values. So it turns out that this is what's called a tab-separated value file. So before we've seen these comma-separated value files, CSV, that's what CSV stands for, comma-separated value. This is a tab-separated value. So instead of using commas, they're using the tab character. And what do I mean by tab character? It's literally the tab key on your keyboard. That's the only difference between our CSV file and this file, is we are using a tab to separate each of the columns instead of comma. So that might naturally raise the question, well, how are we going to bring this into R? How can we write the code to bring in this tab-separated value file into R? And I'm glad you asked, because that's exactly what we're going to do. We're going to see how we can bring this into R. So I'm going to jump into RStudio, and we'll take a quick look. Everybody, just make sure everybody can read the code even at the back. At the back? How's that? Less Cool. Okay. So on line 5, where my caret is right now, line 5, you'll see I'm declaring a variable called lung data. And I'm using our tried and true read CSV function. And I'm giving it the name of the file, lungcapdata.txt. But notice I've got a second parameter called SEP, separator. So it turns out with R, if I use the SEP separator argument, I can tell R how the columns are split. Normally when we run read CSV, it assumes that all the columns are split using a comma. But if I say separator equals \t, I'm now telling R, our columns are separated using a tab character. So instead of separating the columns out using commas, separate them out using tabs. And if I run that line, I will now get a data frame. Again, 725 rows, 6 variables. If I open the data frame, here's what it looks like. So we've got our lung capacity, age, height, whether or not they're smokers, gender, and born via cesarean section. So this isn't terribly different from what we've seen so far. The only major difference is we are telling R to use tabs instead of commas to read our CSV file. Everybody follows along so far? Cool. So if we're creating a linear regression model, actually, you know what? Let me, whoops. So if we wanted to create a linear regression model, it looks like I posted the code a little early, but what the heck. So if I want to create just a linear regression model that compares lung capacity with age, see if there's any relationship between those two. How would I write that code? What would that linear regression model look like? What would I fill in here? Yeah. Yep, so which would be, yeah, so let's take a look. So so the 6 variables I've got to work with. I'll put them on the board here. I've got lung capacity, lung cap, age, height, smoke, definitely don't do that, gender, and cesarean. So those are the different variables I've got to work with. What should my linear regression equation look like in R? So lung cap, that's a good start. Squiggly, known as the tilde. Yep. So lung cap, squiggly. Yeah, let's equate it with smoke. Let's see if there's any. Let's see what the relationship looks like here. So let's create a model. Let's see. Our independent variable is lung cap. Dependent is, or predictor variable is smoke. And here we go. And let's output a summary of our model. I'll bring this code back up here. So we've used our dummy variable already. So let's see here. Actually, you know what I want to do? We'll do age first, and then we'll introduce the dummy variable. I'm sorry, I got ahead of myself. So our model will be lung capacity versus age. We'll output our summary for that. And it shouldn't come as any surprise that as age increases, lung capacity seems to increase as well, and that's significant at, what is that, 0.01% confidence. So, you know, pretty good chance that our model is, and our adjusted R-squared is pretty good too, 67%. So our model explains things pretty well. Seems to make sense. Older you are, more your lungs can actually hold, right? Cool. But we could do better. We could probably explain more of the data if we added some more variables on. So just for a second, let's look at, we're going to use a function called contrasts. And this is going to tell us, and we'll use it for the, let's see, we've used 2 of these variables here, lung capacity and age. So we've got height, smoke, gender, and cesarean left. Yes, we've used lung capacity and age. Let's use smoke as our next variable. Let's do the contrast on smoke. What does this contrast thing do? I haven't introduced it. Let's see. What contrast does, so this is a function that we haven't talked about yet. What contrast does is this tells us for a categorical variable which of the categories is being used as our baseline and which is going to be used as our control. So basically we're going to see, okay, our dummy flag, we're using yes as our dummy. So let's do lung capacity tilde age plus smoke. Let's see what that does. Let's create a model and see what that does. So we'll create that model, we'll do summary, and look at that. Our regression model seems to suggest that if somebody is a smoker, their lung capacity seems to decrease. What a surprise. So everybody follows with that so far? All we did, and again, we haven't had to write any code to give us this category or dummy variable. R has taken care of that for us. Any questions so far? So let's explain a little bit about how the dummy variables work in R. So first off, to have a dummy variable, the column must be categorical. So R must have interpreted that column as categorical. Otherwise, if it didn't for some reason, we need to factorize that column. It uses the first value that it finds in that column as your dummy flag. So if we go back to the code for a second and take a look at our contrasts, we see that R has used yes. R has marked yes as number 1. If we look at our data, let's see here. So R has used our first value, no, in the smoking column as its baseline. It's marked that with a 0, so yes gets number 1. And in this case, I used the wrong example. Let's run this regression, and instead of our regression using smoking, we'll use the gender variable. So we'll do age plus gender. So I'm switching back to R here. I'm going to create a new model. It'll be lung capacity predicted by age and gender variables. And the output of this model seems to suggest that if the gender is male, that seems to be correlated with an increase in lung capacity, in predicted lung capacity. And it's fairly significant. And again, our adjusted R squared is actually even better than than just doing lung capacity versus age. So not bad, right? And if we look at contrast between, if we look at contrast of gender, we'll see that female has been marked as our baseline, male has been marked as our control. So I'm going to keep that code up. I'm going to keep this code up on screen because now it's your turn. So we've got these 6 variables: lung capacity, age, height, smoking, gender, and cesarean. We know how easy it is to create how easy it is to create categorical variables in or add them to our regression model. Now it's your turn. Take a few minutes, work together, and build a few regressions. Do lung capacity versus age and whether or not the person's a smoker, versus age and gender, versus age and smoker and gender, versus all the variables. What factors seem to have the most impact on lung capacity? And also as a bonus, is there any sort of correlation between lung capacity and height or lung capacity and age? And if so, how much? So take a few minutes, work on that together. I'll put the code back up on screen so that you'll be able to mostly read it. And this watch doesn't beep, but time starts now. All right, so talk to me about your findings. What did you find? So lung capacity and height had the strongest association. Interesting. So hey, look at that. I didn't create a model for that one. I'll create a 5th model here: age and height. Height and age and smoker and all that other stuff. So if we look at just my first model here, where I'm just doing lung capacity versus age, I'll create these 5 models. So if I just look at lung capacity versus age, you'll notice that my adjusted R squared is only 0.6714. So again, we only describe 67% of the variance in the data. So if we do model 2, where we add in gender as our dummy variable, we notice that goes up to around 70% of the variance. And we see that gender male seems to have an impact. If we add in gender and smoker, again, if they are a smoker, it seems that their lung capacity goes down. And we also see that the adjusted R squared goes up again a little bit. our fourth model, where we're doing age, gender, smoking, cesarean, we see that cesarean doesn't, again, notice how we don't have much significance beside cesarean yes. So in this case, it is not statistically significant, and we see that our adjusted R-squared is basically untouched. Now, let's throw age into the mix, or let's throw height into the mix, excuse me. So if I do a summary on that one, all of a sudden you'll see that the significance of cesarean yes goes up a little bit, but our adjusted R-squared spikes to 85%, which tells us that between height, age, and gender, it seems like we've got, and smoking, it seems like we've got a pretty good model that explains the variance in our lung capacities. So interesting, isn't it? So we're learning something new about lung capacity today. Not our typical government data. We're now delving into healthcare, but we're now able to actually see, hey, what are some of the impacts of these different control variables? Cool, eh? All right. Who ran a correlation between lung capacity and height? Anybody? What was the correlation you found? So 0.83. So let me see if I can run that as well. Let's see here. Yeah. So if I do, you did it between lung capacity and which? And height. Let's run that. So if I do core lung data, $lung cap, and lung data and height, you found which? Oh, you did adjusted R-squared. Okay. So if we look at the correlation, we see again that lung capacity versus height. We run the core. Remember, COR gives us Pearson correlation. We see that we've got 0.91. So that is a very strong positive relationship, which suggests, again, height has something to do with lung capacity. What if we ran it for age? Anybody want to run the correlation for age? What does that give us? Yes? So again, that seems to have a pretty strong positive correlation, right? So fascinating stuff. So congratulations, we've now used our first dummy variable. How cool is that? And best of all, you didn't have to write any extra code in order to use it. So we're all feeling pretty good about that. Okay. Now, I'm just checking my slides real quick, because I don't want to get ahead of myself. Let's see. Whoops. We don't want to do advanced techniques yet. I'm sorry. Actually, yes, we are doing advanced techniques next. Here we go. Okay. So advanced technique. And these advanced techniques are based on some of the questions that I have received throughout this course. The first advanced technique we're going to look at is to see if we can perform a correlation by group. So for example, we've just run the correlation we just ran between age and lung capacity and height and lung capacity was across our entire data set. Now, it probably stands to reason that because males are human and females are human, that our findings of the older you are, the larger your lung capacity, or the taller you are, the larger your lung capacity, that across human beings, that should hold. But for the sake of argument, let's assume that, let's say, you know what, maybe we need to just validate that assumption. Maybe we've got the really picky, analytical guy that's been sitting in the cubicle at whatever place you're going to work at, and they've been there for 25 years, and they are an old, hardened, bitter programmer. And trust me, you will meet these people. And we need to prove to them beyond a shadow of a doubt that this holds for both data sets. So we can use the by function along with a function that we write in order to find the correlation inside of a group. So how do we do that? Well, our slide gives us the general code. We're going to write this together in R. Ready? Here we go. So, let's write this. I need to move It would really help, too, if I moved R back onto the correct screen so we could write it together, wouldn't it? Ah, Thursday, man. It's like we're almost there. We're almost there at the weekend. It's so good. All right. Here we go. So, our strategy, we're going to find our correlation by writing by, specifying our data frame, specifying the group that we want to use, and then writing a special function that finds the correlation of two variables inside that group. So, let's do this. I'm going to write by, open bracket, and my data frame is called lung data, isn't it? Lung data. And my data frame group, in this case, we'll go gender. How's that sound? And now the function, so I think before we've looked at the by function and we've said we can group we've done a little bit of grouping before, and we've specified something like mean or some other way to say, okay, give me the total number of crimes per fiscal year. Well, what we're going to do is write our first custom function, because if we were to say core right here, R would kind of go crazy. It doesn't know what to do with that. So what we're going to do is say, okay, we're going to write a function, because what R is going to do is for each of these groups, it's going to basically it's going to have as an input to whatever function we would normally call here, a subset of our data frame. So in other words, we'll have just the male data or just the female data. So in our custom function, we're going to say that we're going to call correlation on just this subset that we get, and we'll correlate our lung capacity with our height. And we'll see if this relationship holds. We'll see if this relationship holds across both genders. Ready? Who thinks this will run? Line coding, I'm not referring to my notes here. So it did run. Look at that. I got something right today. Woo! So we see that we have lung capacity. If gender is female, the correlation is 0.904, 0.905 rounded. So there's a strong positive correlation. For male, it's 0.916. Again, strong positive correlation. Yeah? Sure. So the function x, what is this nonsense that's going on that I've just introduced at the 11th hour? So normally, when we're grouping by, what we could do is, and where we've seen this before, is when we do stuff, for example, we want to see what is the average, what is the average of our heights? I think we've done that before. What if I just do sum here? Or actually, yeah, so what's happened here is normally I say by lung data, we do lung capacity. Yeah, here we go. Normally what we've used for by is we've put in the specific column that we want to summarize. And then we've said what group we want to summarize by, and then what function do we want to apply to that group. So in this case, but what's actually happening here is when we're saying what function we want to run, in the background what's happening is R translates this part that I've got highlighted, this fun equals sum, into this. Because what R does in the background is basically for each of these groups, takes a subset of the data frame, or takes a subset of that column that corresponds to that group, and passes it as a parameter over to whatever function we're calling, like sum, like mean. In this case, things are a little bit different. And the reason that is because so notice in line 28, instead of specifying the column that we want to summarize, in this case we're saying we want to summarize the data frame somehow. We're going to do an operation that's going to affect the whole data frame. So we can't just put in core So we can't just say fun equals core. Can't just say function equals core because correlation needs two parameters. So core has no idea what, like core, if we were to just do this, for example, I'm going to copy line 25, or line 26, let me copy this. So if we were to just do the following, what we're passing to core is this. What we would be passing to core in this case is just the subset of the data frame where gender equals male or gender equals female. And so core is not going to know what to do with that because some of those variables are not numeric. So some of the, like, let's see, we have lung capacity and age and height that are numeric variables, but these three, smoking, gender, cesarean, they're non-numeric, they're categorical. So we can't run correlations on those categorical variables. So this is going to barf. What we're doing instead here is saying, okay, we want to have a little bit more control over how R does that summarization. So we do that by saying we're going to write a special function that for the value that gets passed over to our function, we're just going to run our correlation on that subset of the data frame. Good question on that one. A follow-up question you may have is, so we've got this line, we're saying by lung data, we want to group by gender, and our function, we're doing a custom function, and we'll find the correlation between these two variables. Why are we using X here instead of the data frame name? You might be wondering that. Let's try that. So I'm going to copy line 30, I'm going to make a copy of that, and in our custom function, instead of using X, I'm going to use lung data. Okay, everybody follow what I'm about to do. So basically, I'm going to say in here, instead of using this X, I'm going to use lung data, which is what you would expect to use, right? Everybody's expecting that we should use this. But look what happens. When I run line 30, for each of the groups, what's happening is it's running the correlation on the entire data frame, not the subset that has to do with that group. So in this case, I've run the and this confused the hell out of me a couple nights ago. Because I was like, well, we usually use like the data frame name whenever we're in here. But in this case, this X represents the subset of the data frame that has to do with the category variable. So in this case, we use the name of our data frame. We're just running our correlation on the whole data frame twice. And see, we get the same, and suddenly we get the same correlation and things look kind of screwy. So this X represents the subset of the data frame that's been grouped by our gender variable, either male or female. So if I run this again and I use X instead of lung data, you'll notice that I get the correct correlation output. 0.904 female, 0.915 for male. So that's why using X instead of the data frame name at the end inside of our core here is important. We want to work on just that subset, not the whole data frame. Does everybody follow that? Okay. So that, ladies and gentlemen, is advanced technique number 1. Running a correlation by group. So we can use the by function to run a correlation across our entire group. Now, you might also wonder, could we find the average by group? So what is our average lung capacity by group? Or what is our average, what's our average lung capacity by group? What's our average lung capacity among smokers? Wouldn't that be interesting to find? Is there a big difference between the two? How do you think I could run that How do you think I could run an average by the group? If we go back to the code for a second, how do you think we can run this average by group? So instead of function, we do sum. So help me write the code. Assume I'm stupid. Help me write the code. Sum x. So where would I put sum x?
Well, like you just replace, I think you would replace the function, like the blue highlighted function part, for the blue function.
So remember we're just now if we specified which column we wanted to operate on, we could do that. But right now we're using the whole data frame. But you're close though. We want to keep function here. We want to keep fun equals function x, but we're going to replace core with something else. What are we going to replace it with? Well, we want to do average this time. What's the average function in R? Yeah. Mean. Yes. So mean. I mean, R is mean, but that's okay. Okay. And we're going to do mean of what? What are we going to put in the brackets? Specific columns of what? X. Very good. X lung cap. I'll make a copy of this line and we'll run it. Pardon? Yeah. Good catch. So we're going to look at smokers. First we're looking at gender, and we see if we group by gender and take a look at the average lung capacity across females seems to be 7.4, whatever the measurement, I forget the units, and then by male it's 8.3. Now let's take a look at mean across smokers, because tobacco is so much fun. It's is it smoke or smoker? Smoke, thank you. Let's see. Well, isn't that interesting? So the average lung capacity among non-smokers is 7.77, and the average lung capacity across smokers is 8.64. Not exactly something I would expect to see, but okay. Interesting. So those are two advanced techniques. You can correlate by groups, and you can do averages by groups. Correlations by groups and averages by groups. And you've also learned how to write your very first custom function inside of R. Congratulations. Any questions before we move on? Just as an aside, I will make sure that these slides are posted after class. And I've got my mic on today, so this video will actually be posted after class too, finally. Okay. I'm hearing some whispering. Would you like to share?
You were just saying that meant that smokers on average had a larger lung capacity.
Does this mean on average that smokers seem to have a larger lung capacity? At first glance, it would, wouldn't it? Because we're just finding the average of lung capacity across non-smokers and smokers. So, but what we're not doing right now is we're not also saying, okay, well, let's, should we do it across genders as well? Does that hold? Who knows? We could run that another day, but I've got more advanced stuff to cover. But it is interesting to see that on average, in this case, non-smokers seem to have a smaller lung capacity, which is interesting. But again, we're doing the average across the whole data. We're doing the average across the data set, so there might be other factors at play. But what we've seen in our regression analysis is that smokers tend to have a lower lung capacity. Lower lung capacity seems to be predicted by whether or not they're a smoker. And if they are a smoker, it seems to be predicted that they will have a lower lung capacity. So this is an example how just looking at the average may not be meaningful. If we were to actually plot this data, who knows, there might be outliers. Why don't we plot the data? Because you know what? I haven't done that yet, and I'm kind of curious. Let's plot that data. Let's see if Excel will let me open this file. Because there was a piece of, there was a topic I was thinking of covering next week, but maybe we'll move it ahead. All right. So let's see here. Who here has ever, yeah, what the hell, let's do it. Who here has ever used Excel pivot tables? Pivot tables. A few, oh wow, actually that's more than last year's cohort. That's awesome. So if you've never used Excel pivot tables, you are in for a treat. These are used very commonly in the corporate world. Government folks love them. Who wants to explain to me what a pivot table is? Yeah.
Data visualization tool. You just take tables full of messy data and then it creates tables and graphs automatically to make it look nice.
So it gives us a way to do some data visualization, but I would challenge that it cleans up data automatically. Anyone else want to give me a definition of what it, yeah? So we can manipulate the data a bit. What pivot tables also allow us to do is stuff like we can sort and filter our data. We can remove duplicates. Best of all, we can do stuff like create a pivot chart. So right now we've just created a table. If we do pivot table, if I hit summarize with pivot table, I'm going to summarize the table that I just created. I'll get a new worksheet, and now I can see, now I'll say, you know what, I'm going to create a pivot table that I'm going to have rows, and my rows will be smoker, and I'll do lung capacity. I'll set this as my value, and I'll find the average of it. And so again, we see no and yes. Lung capacity, average of lung capacity no is 7.77. Average yes seems to be 8.64. So if somebody's a smoker, seems to be an indicator that they are that they have a bigger lung capacity, which doesn't really make sense. So let's bring on some more values and see if that helps break things down. So let's split this out by gender, then by smoker. Let's see here. So female, let's see. So if we split things out by gender and then by smoker, we see that on average for females, lung capacity is 7.4. But again, it seems like there's something going on here. If they're not a smoker, the lung capacity is lower than if they are a smoker on average? That doesn't make sense, does it? So let's see. What about, we can also drag on other values. For example, we could do like this, our average of height, since sum of height doesn't really make sense. We can also turn this into, we can also quickly chart the data that we've got by using pivot charts. So for example, I'm going to do a combination graph here, and I'll put height on the secondary axis. And we can see that across the two groups, we can see female versus male. We've got our average of lung capacity and our average of height. So it's a really powerful tool. Pivot tables and pivot charts are a really powerful tool that you can use to explore data very quickly. What's also cool about these is when you get into the corporate world or when you get into the government world, you can actually take Excel and aim it directly at a database or a CSV file or any other data source of your choosing and do data visualization and manipulation right inside of Excel. Very important. I definitely encourage you, look up pivot tables and pivot charts, how to use them. But you might be thinking, okay, well that's fine. Could we create a, why don't we actually take a look at this data and see, like, let's plot out all of the lung capacities. Yeah, let's plot out all the lung capacities. Let's see if we can actually make a chart out of that. Actually, you know what? Maybe we'll graph it out later. Or we'll graph it out now. Why not? Give me a recommended chart. So let's see if we do lung capacity, seems like it's pretty randomly distributed. If we do lung capacity versus smoking, though, let's see what that looks like. Give me all charts, and I want an XY scatter. I might not have set up my data correctly, but that's okay. We'll do that part. We'll do that part later. We'll plot that data later. We want to get back to R because we got a few more techniques that we got to get through. So we've done correlation. We've done average by group. Now the next more advanced technique that we'll want to cover is we've taken a look at categorical variables. So we've taken a look at our categorical variables, and we've seen that by default in R, when we read in one of these categories, it uses the first value that R uses the first value that it finds as our baseline. So for example, if we're dealing with dummies here, smoking would be represented, no would be represented with a 0, and yes would be represented with a 1. And we've seen that if we use that funky looking function called contrasts. And again, looking at the data for gender, I'm sorry, I got that backwards again. So the first value that it runs into, it's going to mark as a 1, and then which will be your baseline, and then the rest will be marked with 0. So the first item it ran into for gender is male. First item it runs into is smoker is no. So if we do contrasts on gender and contrasts on smoke, we see for these two levels that we've got female marked as 0 and male, that's our dummy flag. And then for smoke, we see that no is marked as 0 and yes is marked as our dummy indicator variable. But what if you wanted to do that the other way around? What if instead of being female equals 0, male equal 1, you want female equal 1, male equals 0? What if you want to do that the other way around? That you want to set female as your baseline. How do we do that? Well, it turns out that's where the second advanced technique comes in. We can use a function called relevel to reset our baseline. How do we do that? Well, we have to assign a value back into our data frames column, but we use this function called relevel, where we specify the column that we want to reformat, and then we specify what our new reference value will be. So let's do this. So right now we have our contrast. If we look at the gender column, that female equals 0, male equal 1. I'm going to set lung data gender equal to relevel, and our syntax was our column, and then we specify our reference value, lung data gender, ref equals, and we want to set our reference to be female. And now if we look at contrasts, or excuse me, I want my reference to be male so that female is set to 1 and male is set to 0. So reference is set to male now, and if I look at my contrast for gender, so you'll see now male is 0, female is 1. And so if we were to rerun our regression analysis, we'd now be using female as our indicator. Cool, eh? So that's all there is to it. Any questions? Okay, let's keep going. So the next technique we're going to look at. Right now we've got our 6 variables: our lung capacity, age, height, whether or not they smoke, gender, and cesarean birth. Age is a tricky one because what if, for instance, a health minister came to you and said, you know what, in the way that we're funding the way that we want to fund a new program, we want to fund this based on age range. Maybe our age ranges are, if they're 8 or under, that we consider them a child. If they're between 8 and 12, we consider them to be a youth. And if they're between 12 and 19, we consider them to be a teenager. How could we categorize all of our data into these 3 age ranges? In other words, how do we create a new column called age range with these 3 values: child, youth, and teenager. Because then we could run some of our grouping on these age ranges. Because right now we could group by our age range. In fact, I'm not even sure we'd be able to do that because that R is interpreting as a numeric value right now. We don't even have a categorical value for age. So we want to construct a category called age range. So how could we do that? That's where we get into our third advanced technique called if-else. What if-else does is checks a condition that we pass in. If that comes out to true, if-else will return the true value, and if this condition is false, it will return the false value. So let's think about that one for a second. So again, I'll put the age ranges on the board. So less than 8 equals child. If they're between 8 and 12, they're youth. And if they're between 13 and 19, they are a teenager. So let's create this new column called age range. And we're going to use this if-else to write it, to create our column. Ready? So I'll scroll down a little bit. I'll give us some room to work with. I'll hide the version that I wrote before. I'm going to create a new column. Now everybody remembers how we create a new column. We give the name of our data frame, put in the $, and give our new column name. What's a good name for this new column? Age range? Age range. Let's call it age range. So our new column is going to be equal to if-else. And remember, our first parameter is the condition that we're checking. What are we going to check? Let's just write the if-else to say either child or let's just write the if-else that checks for child. So what will this condition look like? Any guesses? Yeah. So lung data, age is less than or equal to 8. Correct. So if that is true, then we want if-else to spit out child. Else, we'll just have it return teenager. Now let's take a look at our age data. Let's take a look at our lung data frame now. So notice we've got one more column called age range. But notice that we only have either child or teenager. Well, we've got some data points in here where the age is 10, and we want that to be youth, right? Any guesses on how we could do that? Yeah.
We do the same thing, being like if-else, lung data, $, age, between 8 to 12 equals youth, or comma youth, and then do else teenage or child.
So we can the key to this is going to be using a second if-else. You're absolutely right. where are we going to put that if-else? Yeah. So after the comma beside child? So we're saying right here? Why don't we try it? So we'll put if, so see what we're doing here. So we have if else here. If our age is less than or equal to 8, we're saying they're a child. Now I'm writing a second if else. And I'll do lung data, age. What will my condition be? So now we're choosing between youth and teenager. We want to return, so we're going to be returning either youth or teenager. What should go where and what's my condition? Yeah.
Less than or equal to 8, greater than or equal to, or less than or equal to 12, greater than 8.
So there's a couple ways we could do this. Let's assume for a second that we can't, let's break these expressions down for a second. Let's assume for a moment we don't know how to chain two things together. Say like, if the age is greater than or equal to 8 but less than or equal to 12. Let's assume for a second we can't do that. So let's, where did my whiteboard marker go? Here it is. So we've got these three conditions. Condition number 1, where age is less than or equal to, or age is less than 8, which is, or actually what we've written is incorrect. I just want to have age is less than or equal to 8, they're a child. If the age is greater than 8 but less than or equal to 12, then they're youth. And if the age is 13 to 19, that they're a teenager. Now, an important part to know is that the upper limit is that our age, the range of values is from 0 to 19. So this only has to do with people that are up to and including 19 years old. So that's the limit on our values. So knowing that, what's an expression that we can write to say that whether or not they're a youth or a teenager? How can we simplify this expression here? Yes? Yep. Exactly. So this really simple, because we're saying that our youth is between age 9 and 12, and teenager is between age 13 and whatever the upper bound is. So really, this simplifies into age greater than or equal to 13, doesn't it? Exactly. So in here, if we write this if-else, we just say if-else, our lung data age is greater than or equal to 13. If that's the case, they're a teenager. Otherwise, they're a youth. Now that line is starting to get really long. I think we can all agree on that. That line is getting long. So in R, when we're dealing with a function call like this, we can actually break this out over a couple of lines, and R will interpret it all as one line. What do I mean by that? If I hit enter right now, I can put this second if-else on a second line. R is going to interpret lines 53 and 54 as one big line. So let's illustrate what's going to happen here. Let me see if I got room to work with. So first, I got an idea. So people in the YouTube video aren't going to see this, so sorry. So what we're doing is for each row inside of lung data, we are going to generate a value for age range. That's what we're doing here. For every single row inside of our data frame, we're going to generate a value for the age range. So let's walk through an example. Let's walk through an example where we're going to say our age in a hypothetical row is equal to 12. So we'll have age equal to 12. So what's going to happen here? So for each row, we're going to go through here. So for our current row, we're going to say if else lung data age is less than or equal to 8. This part here, this lung data age, is going to get substituted with the value 12. Is 12 less than or equal to 8? No. 12 is greater than 8. So this first condition, this child, that doesn't happen. That is not, so because this is not true, 12 is not less than 8, we don't go to, we say, okay, we're not returning child. So we go to this if else. So we plug in where lung data, for lung data age, is 12 greater than or equal to 13? No, it's not. So we skip teenager, our else is youth. So in this case, for this row, we will return youth. Everybody follows that logic? Let's try it again. I'll try it for a different value this time. Let's try it for age equals 7. So age equals 7. So for this row, we'll substitute lung data age, substitute the value 7 here. Is 7 less than or equal to 8? It's not a trick question. Come on. Is 7 less than or equal to 8? 7 is less than or equal to 8. So we're going to return child. So for this row, we'll return child. Let's try one more. We'll try 19, the upper limit of our data. Okay, so again, for this row, we're going to run this if else. We're going to substitute 19 in for lung data age. Is 19 less than or equal to 8? No, it's not. So child is out. Now we're going to plug it in down here. Is 19 greater than or equal to 13? Yes, it is. So we're going to return teenager. Cool? Now, let me throw you a curveball. You ready for the curveball? So we saw our advanced technique 3, which is we were able to use if-else to do 2 different age ranges. Our advanced technique 4 that we just covered is that we're able to chain them together. So we can put if-elses inside of other if-elses, which we tried. And actually, it's about to be your turn again. So, are you ready for your next challenge? Use what we just learned doing if-elses and build some regressions. Now this time, actually, I need to do one thing before I give you your challenge, because we have one minor issue. So remember earlier we were looking at that contrasts function to see like what is our baseline and what is our dummy variable? Everybody remembers that? Yeah? Let's run contrasts on this brand new age range column that we created. So we've got our age range. Let's run contrasts on it. Check it out. So I've got an error. R is giving me an error back. It's saying contrasts apply only to factors. What's that? Okay. What we have to do is we have to turn, because right now we just have we've got a column in our data frame that just contains a bunch of string values. We need to turn those into factors. We need to turn them into categorical data. So how do we do that? So how do we turn that into our into a factor again. Does anybody remember the code that we use? If you don't, that's okay, because I think we covered this like a number of weeks ago. So what we do is we say our lung data age range is equal to as.factor lung data age range. So that turns our data, that turns this column, that's right now just a bunch of strings, into categorical values. And so now we see we've got 3 categories: child, teenager, and youth. So I will leave this if-else code up on screen, but your challenge is we'll take the next couple minutes, and you will, instead of using age, take the regression models that you created earlier, copy them, paste them down here, and instead of using age, use age range. See what difference that makes in your regression models. Yeah? Are
Still giving the same error code after I do that.
Are you? But you're assigning age range back to. So you're assigning the age range column. Have you got an equal sign? Do it again. But the challenge again is the slides say age group. You know what? Just for consistency, I'm going to say lung data age group equals that, and then I'll turn that age group into factors. So I'll run all this stuff again. So your challenge is, again, take this, take a few minutes, build a few more regressions. Instead of using age, use age group. Does that change your regressions at all? And I'll put the code back up so you can see what's going on. All right, so if you use age group in your, or age range, whatever you called it, age range, age group, doesn't really matter. What did you find? The results I found seem to suggest that if you're a teenager, that has a big influence on your lung capacity, doesn't it? Everybody find that result too? Yeah? Same thing with youth. Again, youth seems to have effect on lung capacity. Interesting, though, is that smoking seems to have, that the way that we've constructed our regression model now that we're breaking this into teenager and youth age groups and looking at smoking, we see that smoking seems to have an effect, a negative effect on our predicted lung capacity, but now it's not as statistically significant. Interesting, eh? Funny how the different variables that we add to our model kind of influence how the model turns out. All right, so that is, so we've taken a look now at some advanced techniques. Now we're going to look at advanced technique number 5, which are diagnostic plots. So it turns out that R has some awesome built-in functions to help you figure out if the data that you're looking at has some issues, if it is suitable for linear regressions. How do we do that? All we have to do is call the function plot and pass in our regression model. And it gives us these 4 awesome plots. One of them is residuals versus fitted. One of them is normal QQ, scale location, and residuals versus leverage. Does anybody know what any of those mean? No, shaking heads, looking at that going, this is statistical garbage. So I'm going to let you in on a little secret. I spent way longer than I probably should admit looking up what all 4 of these plots actually do. Because for some reason, statisticians, which is a really hard word to say, but statisticians seem to write in a language that is circular. In other words, you can read the definition of the plot this way, or you can read it this way, and it reads exactly the same. So the next 4 slides represent the sum total of about 7 hours worth of Googling. And when I post the slides, my sources will be posted. That makes it research, not plagiarism. So residuals versus fitted. This helps you to check. All this plot does, after 6 pages of text, all it does is help you check whether your linear relationship assumption is true for your data. And you can see you'll get basically one of 3 outputs. One, which is everything looks pretty random. 2, the variability seems to increase over time. And 3, you've got this parabola going on, which suggests that you have nonlinear data. You want to check for your data being mostly symmetric around 0, or wherever the middle of your data set is. You want to check to make sure that there's no patterns in your data. Again, if you've got this increasing spread over time, or you've got this curved nonlinear spread, that's a suggestion that you have some issues, that your data may not be linear. Oh, do I have to say the heteroscedasticity word? Thank you. You're all smarter than I am. That tells us the variability of a variable is unequal across range. All right, so that is the residuals versus fitted. Basically, if you look at this graph and you see something like this, your data is pretty linear, you're pretty good. The second of the 4 graphs, the QQ plot, that helps you determine if your data is normally distributed. So everybody's familiar with the normal distribution? Yeah, we're all familiar with that, the bell curve-y thing that you all rely on when it comes to exam time during your undergrad? Yeah, the bell curve. This helps you tell if your data is normally distributed. Trust me, in my stats classes, that thing was handy. If your QQ plot is linear, that is good. Your data is more or less normally distributed. If you get a curved QQ plot, so your QQ plot will look something like, and I'll draw this on the, why am I drawing it on the board? I can plot the model. Hang on a second. So let's actually plot the model to see what the QQ plot looks like. So I'm going to plot one of my models here. And let's see, it should give me enough room here to actually see the result of it. If it doesn't, we might have a problem. Let's see. Whoops. Oh, I went too fast. Sorry. Let me run that again. Okay, so for our first, let's see. So our normal QQ, in this case, we see that we've got a pretty linear graph here. So this is a pretty good indication that our data is normally distributed. If this graph were to look curved, for instance, so I'll raise the screen and I'll superimpose a curve over this. Oh, look at that, writing from earlier. So if instead of the graph we see right now, instead we see a curved graph, so something that looks like this, we've got some skewed data going on. So something's not quite, our data is not normally distributed. If we've got heavy tails, so for example, we have data that, we have a graph that kind of looks like this, then that tells us we've got some extreme values that are influencing your model. So your QQ plot is handy to tell you, is your data normally distributed? So that's your second diagnostic plot. Okay. Third time's the charm. Come on, piece of garbage. There we go. That's your second plot. For those of you playing the home game, I was just fighting with the projector screen. Third plot, the scale location plot. So this is used to check the assumption of equal variance. The In other words, is the variance of any residual, or the difference between your observed and estimated value, is that the same across your entire data range? If the case is yes, then you're probably going to be okay, and if the case is no, then you've probably got the hetero thing going on. So that's scale location. And then the fourth is residuals versus leverage. And this helps you identify if there are any points that are in your model that are heavily influencing your model's results. So there's something called the Cook's distance line. And again, it's another statistical term that sort of chases itself when you go and look it up. More or less, what you need to do is if we go back to our models here, and I look at my next plot. Let's see. So I've got my scale location, and that looks pretty good. And if I look at my residuals versus leverage, you'll see that depending on the model that you've constructed, there will be this dashed red line called the Cook's distance, a dashed red line. Usually it appears in the upper right and lower right quadrants of your graph. If you've got data points that are outside of the Cook's distance line, then those points are heavily influencing your model. If you don't, and in this case we don't really have that, then you don't have any extreme points that are skewing your model one way or the other. So those are your 4 diagnostic plots. Your residuals versus fitted, your QQ plot, determine if your data is more or less normally distributed, your scale location, and your residuals versus leverage. What if you want to plot all 4 of those at once? Because notice when I was going through this, pardon? What if you want to plot all 4 of those at once? Well, we can use a function before we plot the model to say how many graphs we want to output at one time. So check this out. I'm going to write a little bit of code here. I'm going to use this function called par. Forget what it stands for. And I'm going to say I want a 2 by 2 matrix of plots. And now when I plot my model, I'm going to get this 2 by 2 matrix of my plots. And if I zoom in on this, so now, instead of hitting enter, 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 enter to see the next graph in that little window, I can see all 4 of these graphs at the same time. So now I can check to see, okay, residuals versus fitted, that looks pretty good. Normal QQ, all right, looks pretty normally distributed. Scale location, all right, yeah, it looks pretty good. And residuals versus leverage, looks like we're pretty good. So these are diagnostic plots that you can use to check to see that your model isn't being influenced too heavily. Cool, eh? That's the last of the advanced techniques that we're going to be covering for R and or at least for regression analysis. Any questions before we move on? Because we're about to change gears completely. Yes? Yep. If you want to reverse the par, what do you mean by reverse? Yeah. So if we want to say, okay, I just want to see them one at a time, I can just say, okay, C1, 1. That gives me a 1 by 1 matrix. And if I hit model, if I plot out my model now I'm going to be prompted to hit enter for each of my different models. Where'd my mouse go? There it is. So now I can see all these plots one at a time. All right. Any other questions before we move on to sentiment analysis? This is where we throw emotions back into the mix. All right. Let's see how much of sentiment analysis we can get through in the next 45 or so minutes, because I can see everybody's had a long week and we need to unwind. And believe it or not, I actually do have a soul. I had to search for it. Apparently, I had signed some paper when I signed some paperwork at the bank, and when I originally picked up my student loans, I guess that somebody got that. Somebody at Scotiabank got to hold on to that, so I picked up the jar and got it back. So it's nice. Let's talk about sentiment analysis. We're changing gears completely now. So we're going to take all that stuff that we've been talking about for regression analysis. We're going to set that aside. Now we're going to do something really cool. We're going to take text and we're going to turn it into data. What do I mean by this? Well, with sentiment analysis, we can take a look at an article or potentially an entire book that's been written, tweets, and get an idea of what kind of emotions would be evoked by those words. What are the emotional associations between the words in the article? What are some of the emotions that might be evoked in the article? So, for example, we'll be able to actually see that we can see, oh, this article has got a lot of words that seem to have a negative connotation, and it heavily outweighs the ones that have a positive connotation. So we can get kind of an idea. As a fun aside, I actually wrote a plugin for Microsoft Word that used a lot of what we're going to do now to actually show me which of my paragraphs seem to be positive, which seem to be negative. I've written entire letters that I thought were like upbeat and positive, and it told me, no, dude, like this is about as depressing as it gets. So sentiment analysis will help us determine that. So this is what we can use to see what kind of bias kind of shows up. You might even be able to use this to see like what are the frequency of certain words. Does there seem to be a certain political leaning to this article? So with some packages in R, we can actually do sentiment analysis pretty quickly and pretty easily. Our strategy is this. We're going to read in our text file. We're basically going to take an article, convert it into a text file, then read that text file into a data frame. Then, with that text file in our data frame, we're going to break it up into what are called tokens. In other words, we're going to take the article and get all the words out of it. Then, we'll take the tokens, the individual words, and we're going to join them up with sentiment dictionaries. And these are dictionaries that have associations between words. It's kind of like a word association game. So if you take the word jump, it might have a active association. And then we will export some of our results, and we'll actually do just a little bit of plotting inside of R to see what kind of graphs we can get out of this. So first thing we'll do is we're going to use a new function to read this file in called read.table. And I'm going to do a little bit of hacky stuff to make this work. We're getting into the territory of unstructured data, and when you're dealing with unstructured data, this is where you might have to employ some more hacky techniques to make things work. There's no shame in that. Nobody's going to judge you on your code. They're going to judge you on your results. The example we're going to use is an article from TVO about the current coronavirus outbreak. And I'm sure everybody's been following that and is scared poopless. So this article, just to pull it up here real quick, this article, title of it, "Will strain our healthcare system. We can't say we weren't warned." This is an opinion piece. And probably not hard to glean that, this is kind of like a, aha, we told you so piece. What I have done, and what you'll see in the Week 8 folder, is that there is a file here called article.txt. And all this file is this entire article with each paragraph on its own line. This is a big text file with each paragraph on its own line. So first off, how can we read this? How can we read this file in? So we're going to do a little bit of hacky stuff to make this work. Let's take a look at how I read this in. So I'm going to switch over here to a different file, and I've posted this already, but you may want to just follow along for the moment. I'm going to run read.table. I just want to explain something real quick in this file when you go to run this on your own computer. I have commented out the first three lines in this file, the install packages lines. So the first time that you're going to run this file, the very first time you run this file, you will need to install the packages tidytext, textdata, and ggplot2. You will need those packages in order to be able to run your sentiment analysis work. Now, on this machine earlier on, I have already installed those packages. Those packages take a while to install. So my recommendation is you are free to follow along, but these packages can take up to 5-6 minutes to install, so you may want to follow along for the time being, and then when I get this video posted to YouTube later tonight, maybe re-watch it and follow along on your computer at home. Because if everybody installs it right now, it's going to slow the network down to an absolute crawl. So first thing I'm going to do is bring in these 4 libraries. Tidy text, string R. Everybody remember string R. This is the thing that we use to do title case, uppercase, lowercase, that stuff. We're going to use the library called diplyr. This is a general purpose library that has a lot of very useful functions. If you get into more advanced R stuff, this library is going to pop up everywhere. And then finally, we're going to use a plotting library called ggplot to do a little bit of plotting of our sentiment analysis. So I'm going to bring in these 4 libraries. I'm also going to clean up my environment a little bit here. So I'm just hitting the, on my environment, I'm just hitting the little cleanup toolbar buttons on my plots and on my environment. That way I've got just a nice clean slate to work with so that the old stuff doesn't get in the way. So first task of mine is to read in this article. And how I'm doing it is I'm using the read.table function. So I specify the file name. I say I'm telling read table I've only got 1 column, and I want that column to be called line. And then what I'm also saying is if there's any spacing at the beginning or the end of any line, strip it out. I'm specifying that my separator is the tab character. Now, why am I doing that? It's a little bit of a hacky workaround. It's because the tab character doesn't appear in any of my lines. If I don't specify this, there's a couple instances where there's quotation marks, there's a couple instances where there's commas. If I don't specify that the separator is this tab character, R will try to separate this out based on the commas or quotation marks or all that other nonsense. So I basically want to put in a character that will not appear in the line at all. That way it'll just read the line as 1 big column. And then finally I'm saying strings as factors. I'm set that equal to false because I don't want R to factorize. I don't want it to consider every line to be a category. I just want the string values because later on I'm going to pass this into the thing that gives us our individual words from this data frame. So there's some hacky workarounds going on. This allows us to read this article 1 as a data frame. So check it out. I've got 10, it says 10 observations of 1 variable. In other words, I've got 10 lines of text. If I look at this data frame, you see I've got 1 column called line, and then I've got 10 lines of text. So like I said, we're using 4 packages, tidy, yeah. Which, the read table? So read table, and I've got a slide about explaining all of this in detail at the end. But basically what I'm doing is I'm setting this up in a way that read table will be told, just read all of these lines in this file as 1 big column. Don't try to, because otherwise R will try to apply some smarts like finding commas and finding quotation marks to try and separate this out into multiple columns. I don't want that. I need a data frame with 1 column that has all of my lines, because I'm going to pass that off to another function later on that just gives me all the words that are in that article. So we're using these 4 packages. We install them. What we're going to do is take a look. What does this sentiment dictionary look like? So I'm going to use this function called getSentiments, and I'm going to use the NRC Sentiment Dictionary. Now, I believe I can't remember if it's the American or the Canadian National Research Council basically came up with an emotional association dictionary. I know the Canadian one did, and I've used that in a different project. But, so if I run this, getSentiments, and I look at the NRC, this gives me a data frame. And we'll see that for every word in here. We see like abacus, abandoned, abandonment. They've all got different sentiments attached to them. So we can see that abandonment seems to have anger, fear, negative, sadness, surprise connotations. And this is repeated for many words inside of this dictionary. And there's many different sentiment dictionaries that you can use. For this example, we're going to use the NRC one. Now, something else we haven't covered to date, or we might have covered it, but we glossed over it. What if for some reason you want to take a look at this dictionary and go like, well, let's just take a second look at this. This sentiment dictionary has got 13,000 different sentiments in it. That's a lot. That's more than I can fit in my head. Wouldn't it be nice to filter this down just to the words that have to do with like joy or happiness? And in general, wouldn't it be handy if you could filter your data frames through R? Well, it turns out you can. We can use something called the filter function to filter our rows where a certain condition is met. So in this case, we can use filter. If we do filter NRC where sentiment is equal joy, oh, what's going on here? Anybody see this character? Anybody know what this character that I've got highlighted is? What that's called? That means or, very close. So this is called, the pipe character that I've got selected, this means or. So what I'm saying is filter the NRC data frame where the sentiment is joy or the sentiment is disgust. So check this out. I'm going to say NRC joy equals filter NRC sentiment equals joy or disgust. And this now gives me a filtered data frame. It's got much less items now. What is that, 1,200 or so? And we see that this new data frame only has words where the sentiment is disgust or the sentiment is joy. You could just as easily apply this to data frames that you're working with in your projects. For example, we could use this to filter down our lung capacity data where age is greater than 13, or where smoker equals yes. And we can join up a bunch of these conditions by using ands and ors. How do you do that? Well, maybe not so surprisingly, if we want to and two conditions together, where age is equal to 13 and smoker equals yes, we use the ampersand to say and. So both sides of this must be true. In order for this to return a result, both sides must be true. We can use or, where we say one or both of these sides can be true, and it will return. Then, say we want to negate that whole expression. So we want everybody who's not 13 and is not a smoker. We could say, give me everybody that is 13 and is a smoker, close that in brackets, and put an exclamation point in front of it to say, invert that. Give me the case where that's not true. And then how do you do your conditionals? How do you actually do your comparisons? Two equal sign says where two things are equal to one another. Exclamation point and an equal sign is not equal to each other. Greater than, the angle bracket is your greater than. Angle bracket plus equal sign is greater than or equal to. And then less than, left angle bracket, and equal sign is less than or equal to. So those are your conditionals and how you can filter data frames. Any questions? Okay, let's keep moving. All right, so let's get back to our data frame here. So again, and something I want to point out here is that this line kind of looks a little bit weird, right? We're doing read table, but instead of having a line that kind of goes all the way off to the right-hand side of the screen, I've got article 1, and then the column names, and then fill, and then strip white, and then the separator, and strings as factor. They're all on their own lines. Well, because we're calling a function, we're dealing with these brackets, R knows that until it hits this end bracket, interpret all of this stuff as one big line. So this helps when your lines start to get really long across the side of the screen. You can start breaking them up using the Enter key. Okay, so I've read in my article. Now, I want to turn this data frame of mine that has the article into tokens, or the individual words that are inside of my data frame. And we're going to use a function called unnest tokens to turn this entire article into a one-column data frame that has all of my words. So let's do this. So I've already done my read table. So I'm going to do article tokens. I'm going to create a new data frame here called article tokens. I'm going to set it equal to unnest tokens. I'm going to pass in the article that I've read from up there. Now you'll see that I've got word and line. What are these? Well, the way that unnest tokens works is we're basically saying that this is the name. This is going to be the column name that represents each column, the column that contains all my words, and this is the column that we're going to read all the words from. So check this out. When I run this function, I get a new data frame called article tokens. And I now have a list of all the words that appear in this article. So I now have a unique list of all 837 words that appear in this article. So now that I've got a list of words, now we can join this up, or how do we combine two data frames in R? Merge. Very good. We can merge these two data frames together. So remember, I've got my NRC sentiment dictionary. That's a data frame. I've got my article tokens. That's a data frame. But what if we try, and just to double check what our data frames look like. So I've got my article tokens. It's one column, and its column name is word. And if I look at my NRC sentiment dictionary, I've got a column named word, and I've got a column named sentiment. Now remember that the way merge works is that it's going to combine the two data frames based on the names of the column names in the two data frames that are the same. Everybody remembers that? Let's try it. Let's try this. Let's create a new data frame called article token sentiment, and we'll try to merge article tokens and the NRC sentiment dictionary. So let's try that. And we've already got an NRC sentiment dictionary already exists in the data frame called NRC. So let's try this and see what happens. So article tokens sentiment, when we do our merge, worked. So last night it didn't work because, so I was setting this all up for this wasn't going to work, but of course my setup backfired, and this did work. And the reason that it did work is last night I was using a different sentiment dictionary. And what was happening was in this different sentiment dictionary is that we would have, there were a few words that had multiple sentiments associated with them. And the merge, and basically R would say, you know what, no, dude, I can't merge on that. I don't know what you're going to do. So I had to use inner join from the dipleer package, but now because of the sentiment dictionary I'm using, merge totally works, which screws me over for my demo. But that's okay, because in this case, we can still introduce the inner join function from dipleer, which is a little bit more powerful, runs a little bit faster when you're dealing with hundreds of thousands of rows of data. And now dipleer, just to formally introduce it, they call it a grammar of data manipulation. It's basically a package that has a lot of really useful functions that as you get more and more advanced with R will come in very handy. Stuff like anti-merges, and there's a way to basically pipe results from one function to another. It's very powerful. How interjoin works from dplyr is interjoin basically works the same way as merge does. It'll try to merge based on column names that are the same. Otherwise, you can specify the column names that you want to merge on. But in this case, our merge actually succeeded, so go us. So what does that actually look like now? So we can see our article token sentiment. We can see for each of the words in our data frame, we can now see we've got, okay, word, bank, trust, case, negative, fear, sadness. So now we can actually see kind of a frequency of what we can actually start to see some emotions that are being evoked inside of our inside of the article. So wouldn't it be cool if we get the frequency distribution of our sentiments? So we can use the count function to count and get our sentiment frequency. Let's take a look at that code. I'm just going to grab the piece that I made earlier, and we'll use it here. So we have article token sentiment. What I'm going to do is so we can do count. We can do two kinds of counts actually. We can do a count of we can get an idea of the sentiments. We can also get a count of words as well to see what are the most commonly appearing words in our data frame. So for example, I'm going to do count words to create a new data frame that gives me how frequently do certain words appear. No surprises, the word the appears a lot. We see that health shows up 7 times, care shows up 11. What else do we see in here? Capacity, hospitals. No surprising, hospital shows up a couple times in a medical article. Who knew? I feel like I left out some code here. I may have left some code on my computer at home, so I will make sure that gets posted to learn. But it looks like I've left out some code, unfortunately. But I think we can still do a little bit of counting here. So let's do count sentiment. And we'll do it on article token sentiment. And we'll do this on what's our sentiment? Oh yeah, our sentiment column is just sentiment. This should work. No, vars is unknown. Whoops. What have I done? Oh, whoops. I need to pay attention to which data frame I'm using. There we go. So, just to clarify that one. First, I pass in the data frame. Second, I say which variable I want to do my count on. And third is to say I want to sort this from greatest to least. If I look at count sentiment, I have the summary of my sentiment. So positive, oddly enough, is at the top with 33. So our overall sentiment of the article seems to be a positive one, but negative is there's 28 words in there that are appearing that seem to have a negative sentiment associated with them. So positive and negative seem to balance themselves out. So what's the author getting at? Is coronavirus a good news story or is it a bad news story? Does he have a good opinion or a bad opinion? Well, seems to be a lot of sadness, surprise, anger, and disgust, along with a healthy dose of fear. So, maybe he's trying to scare us. But this, in a nutshell, is what sentiment analysis is all about. It's being able to take some text-based data and turn it into a new data format that you can analyze. What is the sentiment that this is giving off? Is this a positive association? Is it negative? One area where you will see sentiment analysis pop up is in stuff like feedback surveys. So if you use sentiment analysis on feedback surveys, you can actually get an idea like, are people having a good time with your product? do they feel that customer service is good, poor, or otherwise? So it can be very good for helping spot some trends in text-based data that you get back. It does have some limitations, and this isn't the be-all end-all. Like, we still need to interpret this data. The computer can just tell us what the associations are. The other limitation we've got here is that sentiment dictionaries are limited. So if you look at the NRC dictionary, we've got 14,000 words, but many of those words have multiple associations. So if you figure the average word has 5 associations in that dictionary, we divide 14,000 by 5, that reduces the dictionary size very quickly. So the R can only give you associations that it knows about. So there might be some very powerful language in this article that truly, to a human being, will evoke fear, anger, uncertainty. But if it's not known in the sentiment dictionary, then all bets are off. You will not get that result here. So there are some limitations. Yeah?
So this sounds like a tough question. So would we use this tool to kind of narrow down a bunch of, like, maybe 17 commentaries that we're looking for, and then we go in ourselves and figure it out to, like, report back? Or, like, can we just reliably say, like, based on this dictionary that we learned, these are the sentiments?
So can we just rely on the dictionaries to say these are the average sentiments, or should we? Or when you talk about narrowing down, like, give me a context.
Let's say, like, this is like a feedback form, or like this is like social media posts that we all compile.
Right.
And then we just said, give me the social media posts that are the most that hit the hardest for negativity. Then we go into it ourselves and say, okay, of the top ones, this is what we find, and then we give the results. Like, is that like kind of
So that's one approach you could take, is to basically say, like, I've got 200 social media posts. Let's see what the average sentiment of each of these posts is, and then, here are the top 10 negative posts. Let's see what they're saying, and then from there, it's, can you spot some trends that are coming up? Like, if you've got companies do this all the time with their customer service surveys, where they see, like, okay, if we survey 1,000 people and we see that the words poor customer service or sucks comes up very frequently in these reports, then chances are we've got a problem. This is telling us of a trend. So even before you go into the sentiment level, where you're saying here's the emotions that are being generated, or that are being implied, you could go in and say, let's just take a look at the word frequency. So if we see the words like sucks, poor, awful, we know that's probably an indicator that something's wrong. But if we see words like good, awesome, wonderful, then something's probably going right, and you want to go in and figure out, like, what made them react that way. So this can help give you kind of a starting point. Techniques like this can help give you a starting point for what kind of emotions are being evoked. So that's when you might want to use sentiment analysis. And what I was hoping to prepare, I didn't have time to get it done this week, but it is possible to use tools like Python and R to automatically download social media posts and then do sentiment analysis on a whole group of them. So you can imagine how useful that would be if you could basically just monitor a particular hashtag and then see, okay, let's take a look at this. Messaging, and you see, like, what bias might a news outlet have? Like, no surprise, Fox News is kind of biased to the right and CNN's kind of biased to the left. Even though they say they're not, they are. We can see that if we see that, okay, CNN posted this hashtag, and they seem to have positive associations with this hashtag, like on healthcare or Bernie Sanders, and Fox News has a lot of negative on Bernie Sanders. Like, well, guess where their political sympathies lie? So it is a tool that you can use to help figure out the kind of starting points. And I want to emphasize the point, these tools are not a substitution for your thinking. Your role in all of this is not to come up with a R script or a Python program or anything like that gives you the be-all, end-all answer to the universe. This is a tool to extract data from an unstructured source, like a text file, a news article, a social media post, and then give it context for the rest of us. Like, we see that there's, like, some negative and fear associations going on, but what does that mean? Should we go into this article in more detail? So that would be my suggestion. I should see if I could dig up that word plugin, because it was really handy for that sort of stuff. The other thing you can do, yeah.
Does this type of thing take into account like sarcasm, for example?
Not really. That's a big limitation, and we saw that with stuff like IBM's Watson. Did everybody watch Jeopardy back when IBM brought on their Watson supercomputer to compete against Ken Jennings and the other guy? That was fascinating, because the first round of Jeopardy, when they brought in IBM's Watson, this supercomputer that was able to play Jeopardy, in the first round, Watson absolutely crushed the human opponents. But in the second round, in Double Jeopardy, if you go back and watch it, what you'll notice is as the clues got clever, like with sarcasm or very short clues, Watson sucked. Because Watson was using sentiment analysis and some lookups to basically figure out, it's like, okay, so we've got this clue, it has to do with Keanu, it has to do with like movie and date and everything. Okay, we're talking, and the category is all about actors, Keanu Reeves, got it. But then as the categories came down to like 2 or 3 word questions or just super sarcasm that you need to be a human to understand, Watson's confidence level went from like 95, 98%, like down to 10. It was incredible. So sentiment analysis, a very important point, is it does not take into account stuff like sarcasm. You may be able to, over time, you may be able to construct a sentiment dictionary that maybe looks for stuff that could be indicators of sarcasm, but like any but it is a text-based medium. So you are limited to whatever text can give you. So and whatever you can basically parse out using a fixed dictionary. Now, it is possible, depending on the technology that you use, if you're dealing with voice data. So, for example, Microsoft has an Azure cognitive service that you can give it a audio file, and it will identify the speakers and what it thinks the emotion of the speaker is. So for a particular part in an example of this is actually in phone calls. So call centers will use this all the time to take transcripts of your phone call with them and use it in training. What it can do somewhat reliably is say, oh, during this time slice, the customer sounded angry. And the dead giveaways for angry is the volume goes up. Like usually when you're angry on a phone call, you get louder, right? Or you get sterner, or your words get more crisp. So we can use some artificial intelligence to kind of detect that. And so we're getting better at it, but for subtle nuances like sarcasm, we're still having trouble parsing it out. Yeah? Sentiment analysis for emojis. I'm not aware of any. I'm sure that would probably help change things, because it is a new way of communicating through emojis. Not new. We've been communicating with hieroglyphs for a long time. But it would be interesting to see if sentiment analysis plus emojis would result in more accurate analysis. Any other questions, either to do with sentiment analysis or more theoretical stuff? Going once, going twice. Seeing none. Just to recap what we did today, we took a look at how to do dummy variables. We took a look at how to do some basic sentiment analysis. All the code from today is going to be posted to Learn so that you'll be able to follow along. I will also post this. I've got this video recorded to my cloud backup for sure this time. So it will be posted to YouTube. I won't need to edit it, so it'll be posted to YouTube sometime later, either tonight or early tomorrow morning, so you can re-watch this. Just as a reminder, Next week, we'll be taking a look at Python, and we'll do a little bit more stuff in Excel, just to show you what you can do with it as a visualization tool. And then the week after, you'll do your second workshop. How that will run is, and the Assignment 2 workshop is now out, how that class will run is you'll have the first 2 hours to do any final preparation, any final work that you need to do, and then at the end of class, you will do your presentations. All right? Seeing no questions, that's all I've got prepared. I'll stick around for a little while. Other than that, have a great weekend.